Good morning.
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 Hi.
Morning.
Good morning.
Good morning.
Morning.
Hi.
Can you start?
Yeah.
Okay. Distinguished guests, experts, ladies and gentlemen, welcome to the CAE ANI joint webinar on food research and technology. I am today's host, Yunfei Xie, Deputy Dean of School of Science and Technology in Jiangnan University. Following 3 successful sections focused on food nutrition and probiotics, green food chains, and food safety and quality control, we are pleased to convene the 4th joint webinar themed New Food Preservation Methods. Food preservation is essential for stabilizing supply chains, reducing waste, and ensuring food quality and safety, representing a global research priority. Advanced technologies such as non-thermal processing, natural antimicrobiology agents, nanotechnology, and smart packaging are rapidly evolving, offering new solutions for efficient preservation and sustainable development. We have invited leading experts from both sides to share cutting-edge advancements in the field. At first, we will now begin with an opening address from Professor Sun Xiulan, Dean of School of Science and Technology, Jiangnan University. Let's welcome.
Okay, everybody, good morning and good evening. Yeah, it's my pleasure to give the address. Distinguished President Oscar Vignet of the National Academy of Engineering of Argentina, Dr. Nomi Zarataki, and all experts. Good morning and good evening to everybody. Yeah. First of all, on behalf of the School of Food Science and Technology of Jiangnan University, I warmly welcome experts from China and from Argentina to join us online for discussions in food science frontiers. I also extend sincere appreciation to both teams for their hard work in organizing this webinar series. Today, I think it is the fourth time, we opened the 4th session focusing on new food preservation methods, a vital topic closely linked to the industry efficiency and also the resource sustainability. Food preservation directly under supply chain resilience, resource conservation, and quality assurance, representing the key technical field supporting high-quality development of the modern food industry. With global consumption upgating and green development demands, diverse new preservation technologies keep evolving and also offering innovative approaches to extending long shelf life and reducing losses and enhancing safety and quality. So we look forward to open discussion about the cutting edge findings, exchanging practical experience, exploring our development of trends, especially building the consensus and pooling strengths to jointly advance in our food innovation and also break through the industrial application of food preservation technologies. So this webinar will further enhance academic exchanges between China and Argentina in the field of food preservation, facilitating the sharing of technical experience and also academic and also mutual learning of research ideas. Taking this webinar as an opportunity, the School of Food Science and Technology of Jiangnan University We are also we have the academic exchange platform, and we will continue to strengthen communication and also collaboration with Argentine counterparts and jointly promote the steady progress in food preservation related research. Finally, I wish the fourth session of the joint online webinar on food science and technology a complete success.
Thank you.
Thank you.
Thank you, Professor Sun, for your
Thank you.
inspiring remarks. Next, let's invite Mr. Oscar Wagner, President of ANI, to deliver opening remarks. Welcome.
Oscar Viñer. Oscar.
Good morning. Good morning to China, or good afternoon. We are very happy to have this seminar between China Academy of Engineering and Argentine Academy of Engineering through SIDCA and Jiangnan University. Today we have a new chapter in food preservation. It's one of the key elements of food technology, and I think this will be a very successful seminar. So we are very happy that we have very important people to have this seminar in Argentina and in China. Welcome, and thank you very much for your participation.
Thank you. Thank you very much for your speech. And next, allow me to introduce the distinguished leaders and guests joining us from China. I will share my screen. Just wait. The first one is Professor Zhang Min. He is a distinguished professor at Jiangnan University. He serves as president of International Research Association for Drying Science and Technology and is a founding fellow of International Academy of Drying Science and Technology. The second one is Ms. Du Fenglin. She has served as CEO of Shanxi Lead Food Flow Technology Company, and she is a graduate of Aston University, UK, and is specialist in corporate management, operations, and marketing. The last one is Dr. Yu Zhilong. He is also from Jiangnan University, associate professor. He received his PhD from the University of Missouri and completed postdoc training at the University of British Columbia and Georgia University. And he is also an associate professor at Jiangnan University. Okay. Next, let's welcome ANI representative to introduce the participants from Argentina.
Margarita está el líder.
One moment, please.
Yes. I have recorded a video with the CV of the participants.
Welcome to our fourth joint webinar on food research and technology about new preservation methods, organized by the Chinese Academy of Engineering and the National Academy of Engineering in Argentina. It is my great pleasure to introduce the speaker from Argentina who will give their lectures today. Our first speaker is Dr. Ariel Vicente. He will talk about radiation manipulation and ozone treatments to reduce fruit and vegetable waste. Professor Ariel Vicente is principal researcher in CONICET and full professor in agroindustry and post-harvest technology at the University of La Plata and the Catholic universities in Argentina. He is an agronomic engineer and owns a PhD in chemistry at the University of La Plata and a master in science at the University of California, Davis, United States. He is a co-author of 90 publications in international recognized journals, including Science, Proceedings of the National Academy of Science in the United States, Plant Physiology, Journal of Experimental Botany, and Post-Harvest Biology and Technology, among others. He has made around 300 presentations and keynote talks in congresses. He has also 50 postgraduate courses in Argentina, Spain, United States in post-harvest processing and storage of fruits and vegetables. He has been editor of the Journal of Experimental Botany, England, and Post-Harvest Biology and Technology. His group is interested in the identification of factors contributing to fruit and vegetable deterioration and finding strategies to control it with the final goal of reducing food wastages. Our second speaker is Dr. Natalia Serman. She will talk about application of direct and indirect non-thermal plasma strategies for the development of ready-to-eat foods. Dr. Serman is a food science specialist graduate of the National University of La Plata who has developed her career at INTA, National Agriculture Technology Institute, since 2004, currently serving as a researcher in the Food Technology Institute. Her professional work combines scientific research as an adjunct researcher at CONICET and INTA with academia as a teaching assistant at the National University of Leuven, focusing her studies on the application of thermal and non-thermal technology to create healthier, high-sensory quality, ready-to-eat meat products, as well as the valorization of livestock byproducts and the mentoring of new researchers through technological outreach and cooperation projects. Our third speaker is Dr. Sergio Baudaña. He will talk about high-pressure processing in Argentina, research and development case studies, and industrial perspectives. Dr. Baudaña is chemical engineer and PhD in chemical engineering, both degrees obtained from the School of Chemical Engineering in the National University of Litoral. He has served as director by competitive examination of the Food Technology Institute of INTA since 2015 and as director of the Institute of Science and Technology of Sustainable Food System, a joint research unit of INTA and CONICET. He is principal researcher at CONICET and full professor of fruit preservation process in the Food Technology degree program at the Institute of Biotechnology, National University of Hurlingham. Since 2021, he has been academic director of the Master Program in Food Technology at the Buenos Aires Regional Faculty of the National Technological University, where he has also served as professor of food preservation and packaging and chemistry, and also of technology of meat and related products. He has published 70 articles in peer-reviewed international journals and 32 articles in national journals. He is co-author of 5 books, 8 book chapters, 1 international patent, and 1 national patent. He has also published more than 150 conference abstracts presented at international and national scientific meetings. He has supervised 8 doctoral theses, 3 master theses, and 15 undergraduate theses. He is director of national and international research and development projects. He has served as a consultant for advisory studies commissioned by the Ministry of Science, Technology, and Productive Innovation. His main research interests include the application of thermal and non-thermal technology in food processing, with particular emphasis on food preservation and product development, using thermal technologies such as pasteurization, sterilization, vacuum cooking, and non-thermal technologies such as high-pressure processing, gamma radiation, cold plasma, chemical compounds, and bacteriocides.
Okay, on behalf of the organizing committee, I would like to thank all the guests for your strong support and thank all the experts for your presentations sharing in the coming webinar. Let's move into the main segment of our webinar, the research presentations. I'd like to invite Professor Zhang Min to begin.
To present at the China-Argentina joint webinar. Today, I would like to share current status, progress, and trends of fresh fruit and vegetable packaging. First, let's take a look at the current status and market demand. Let's first examine the current status of the industry. Globally, the annual output of fresh fruits and vegetables is approximately 2.4 billion tons. China leads the world with about 1.2 billion tons. Argentina is also a major producer, contributing around 35 million tons annually, ranking it among the top producers in South America. Despite the large scale of this industry, we face a significant bottleneck, high loss rates. In developing countries, this figure remains rather high, normally exceeding 20%. Now let me share some news regarding high-value preservation in China. Chinese government has recently launched a new national key R&D program led by China University and involving 25 professor-led teams from all China. Alongside extensive international cooperation, with a total budget of 52 million RMB, this project provides a unique platform to investigate and advance these emerging preservation technologies. Turning to the key projects progress, we have made breakthroughs in both functional materials and equipment. Specifically, 15 new composite materials for smart detection labels have been developed, along with 14 sets of novel smart detection devices for fresh fruits and vegetables. Industry demand is primarily driven by two factors, quality and quantity. Regarding quality, we must meet the requirements for high-value preservation throughout the post-harvest supply chain of fresh fruits and vegetables. Regarding quantity, we must respond to the dynamic scale of sales, meeting the timely demands of both online and offline markets. Therefore, to develop a successful preservation packaging solution, we must address these urgent industry needs in terms of both quality and quantity. Next, I will transition to two representative high-value preservation packaging technologies. One is modified atmosphere packaging, or MAP for short. The other is smart packaging for foods, briefly SPF. Next, I will introduce the current hotspots and the recent progress in MAP technology. To date, MAP has been extensively researched and has been successful application in preserving a wide range of fresh produce, including fruits and vegetables. Also, the associated costs remain competitive and acceptable for industry application. Currently, R&D hotspots in this field primarily focus on synergistic methods and technologies. This includes the synergistic application of physical fields, nano antimicrobial agents, and other integrated approaches. Now let's turn to the first hotspot, the synergy between MAP and efficient physical fields. Recent studies have reported the synergistic effects of over 10 different physical fields, including LED lighting, electrical and magnetic fields, plasma, laser, and ultrasound, on extending the shelf life of fresh fruits and vegetables when combined with MAP. This area of research is currently experiencing rapid growth. Here is a research example from our lab, demonstrating the synergistic preservation effect of LED illumination combined with MAP. We found that the combination of red and white LED illumination with MAP extended the shelf life of Chinese cabbage from 20 days to 30 days under a storage temperature of 4 degrees. Moving to our second case study, we explored the integration of MAP with electrostatic field technology. Our findings indicate that this combination significantly enhances preservation, extending the shelf life of Chinese cabbage to 40 days at 4 degrees. The third research example explores preservation using a photocatalyst in combination with MAP. We found that photocatalyst film activated by LED radiation and combined with MAP extended the shelf life of white mushrooms from 6 days to 15 days at a storage time of temperature of 4 degrees. This research example focuses on laser micro perforation technology combined with MAP. By utilizing laser drilled micro holes in the packaging, we successfully extended the shelf life of fresh cut carrots from 10 days to 18 days. The second R&D hotspot is the synergistic effect of MAP combined with nano antibacterial agents. Due to their remarkable antimicrobial properties and ease of application, nanomaterials have attracted significant research attention. Consequently, integrating these agents with MAP represents a new direction for practical applications. I would like to present two research examples from our lab. The first example focuses on synergistic preservation of fresh cut oranges using MAP combined with nanozinc. We found that synergistic treatment extended the shelf life from 10 days to 18 days under 4-degree storage conditions. The second research example focuses on synergistic preservation of fresh cut potatoes using MAP combined with nano composite coating. We found that the joint treatment of epsilon polylysine catisan composite coating with MAP extended the shelf life from 9 days to 15 days. Next, let's turn to hotspots and cutting-edge advancements in smart packaging for foods. The global market for food smart packaging is growing steadily year by year, boasting an annual growth rate of over 10%. Current R&D hotspots primarily include freshness indicate packaging, intelligent and active dual function packaging, and machine vision for food freshness recognition. The first R&D hotspot is freshness indicator packaging. The core principle relies on intelligent labels or specific zones embedded within the packaging. These zones undergo visual changes to intelligently monitor information related to the freshness of perishable foods. Here, I will present a research example, the development of smart packaging labels sensitive to freshness-related gases, such as carbon dioxide and TBBN. These labels enable triple-edge visual recognition, clearly distinguishing between fresh, sub-fresh, and spoiled state. The second R&D hotspot is smart and active dual function packaging. The core concept lies in the integration of intelligent and active functionalities through the synergy between them to maximize preservation effect. Here I present a case study on fish freshness monitoring and regulation achieved by integrating intelligent and active dual function packaging. The third R&D hotspot is the machine recognition of packaged food freshness. The key innovation here is a shift from mere visual analysis to automated machine recognition. This transition enables us to provide digital prediction and early warning services for food quality and freshness. Here is a research example focusing on the freshness monitoring of prepared dishes based on digitalized data. The following image illustrated our pilot-scale trials conducted in the cooperation with an industry partner. Now let's move to the final part of my presentation. the opportunities and the challenges. We can summarize the future of fresh produce packaging into 3 key trends: diversification of materials and functions, the rise of intelligent systems, and a focus on practical application. However, 3 trends also bring bigger challenges. First, from material and technology. A diversification of food types demands breakthroughs in packaging materials, which is difficult to achieve. Second is from integration. Intelligent packaging must overcome the challenge of adapting complex technology to diverse product characteristics. The third is from commercialization. The practical application of new technologies must balance user convenience with strict cost control. Finally, I would like to express my sincere gratitude to our group members for over 30 years dedicated effort in this area. I'm also deeply thankful for the generous funding support from the China National Key R&D Program, as well as invaluable support from leading Chinese enterprises in this sector. To conclude, our mission is clear: high-value preservation packaging, making fruits and vegetables much fresher. Thank you.
Thank you, Professor Zhang, for an excellent presentation. Next, I would like to invite Dr. Aero Vicente for his presentation.
Good morning. First of all, I'd like to thank Dr. Noemi Sariski for the invitation to participate in this webinar series. Today I'm going to be talking about visual and UV radiation manipulation and also treatments to reduce fruit and vegetable waste. So we probably all acknowledge that food waste is a real shame of our current global food production system. So in the last few years, there have been kind of several strategies to try to control this problem and to tackle food losses. Today I'm going to be commenting about 3 strategies in which we have been working on, which are first the use of UVC treatments, exposure of fruits and vegetables to ozone, and finally the incorporation of pre-harvest nets in the field. So our first case is going to be related to the use of UV radiation in post-harvest. We all probably know that UVC radiation has known germicide effects, and this can may be useful to control post-harvest pathogens. However, we started to work a few years ago on UVC radiation of fruits and vegetables to try to understand a little bit more how these treatments are working. So we wanted to know first if, in addition to the germicide effects, the radiation was having any impact on fruit ripening and senescence. Another question that we wanted to answer was related to the identification of the key factors that are determining the efficacy of this technology. So here I'm showing you some results of work we did some years ago on strawberries, trying to evaluate the use of UVC radiation. So on the left, you can see that clearly the treatment that we use, especially the dose and intensity that we apply on the fruit, are key variables determining the efficacy of the treatments. So certainly here, under this condition, we were able to significantly reduce the incidence of both harvest pathogens. But another treatments here with lower intensity or different doses were not as efficient. So certainly these are two key variables for any UV post-harvest treatment. On the right panel, you can see one interesting result that is showing us that the effects of UV radiation on fruit is much broader than just a germicide effect. So here I'm showing you that the firmness of the fruit along post-harvest storage is maintained when you subject this fruit to a UV-C treatment. So then this is showing us that there are very important effects that are induced on the fruit itself. Some other effects that are we have described on strawberries is related to an improved maintenance of color, either of the calyx of the fruit or of the receptacle. Here, the white bars represent the control, and the gray and dark bars represent different types of UV treatments. And certainly it's clear that UV exposure, in this case, all the treatments were beneficial to improve the score that the consumers were giving to the calyx and to the receptacles. On the right panel, I'm showing you results from an early work we did on, in this case, on broccoli inflorescences, showing that when we expose this product to UVC radiation, there's a strong inhibition, in this case, of an enzyme that is related to chlorophyll degradation. So this is showing us that actually the UV radiation is affecting the product physiology. So trying to, in the next few slides, I will try to summarize the main mode of action of UV treatments. On the right side, you can see the effect, and again on strawberries, on mold and yeast counts of control or UVC treated fruit along storage. So in this treatment, it's kind of interesting that immediately after UVC radiation, we didn't find any reduction in the viability of the fungi. However, along storage, after 4 or several days, we clearly saw that there was a reduction in the microbiological count. So certainly there was something going on that was affecting the viability or the ability of these microorganisms to grow or to multiply. So on the right panel, I'll give you results from another experiment that we did, in this case with Botrytis cinerea. It's a fungi that is very problematic in strawberries. And in this case, we did a kinetic of the germination of the fungi conidia or spores a long time. Okay, so these were conidia that were exposed to UV radiation, heat, or the combination of both, and we follow how these spores were germinating after being exposed. And it's clear that there is a kind of a delay in this or a reduction in the speed of germination of this conidia. So this is one of another effect that UV is causing. In this case, we were not reducing the viability of the conidia. All of them were able to germinate, but there is a reduction probably in the virulence of the fungi when it tries to grow in the fruit. So there are many other effects that are induced by UV radiation. Some interesting ones are related to the activation of defense mechanisms in the fruit. So here, this green fluorescence is showing the induction of one group of phenolic compounds that are antimicrobials and that are accumulated in the epidermis. In this work, we show this on peppers. So there's a strong accumulation of these antimicrobials on the fruit surface, and this probably contributes to the effects that we see in terms of post-harvest disease control. Finally, on the right panel, I'm showing you the activity of one enzyme which is called polygalacturonase. This is a cell wall degrading enzyme. This is involved in pectin degradation. And you see that in the control, there is a rapid increase in polygalacturonase activity during storage. But when we subject this tissue to different kinds of UV treatment, the enzyme is inhibited. So this probably is another mechanism by which UV treated tissues have a better response against pathogens. So as a main conclusion for this third story, we can say that UVC can improve fruit and vegetable storage. And if we want to do this kind of treatments, we have to consider the product we are treating, the ripening stage, And on the side of the process itself, we need to define which is the correct dose, the intensity, and then the number of treatments that we may want to apply. So I'm going to move on now to a second kind of treatment. These are ozone post-harvest treatments. Probably you know well that ozone is a very strong oxidant that has been used for vegetable disinfection. However, there is another interesting use in post-harvest of fruit and vegetables, which is just injecting the ozone gas on the cold storage when we want to store the fruits. So in this where we wanted to know which is the actual mechanism by which ozone is acting on the post-harvest storage of these commodities. So we choose, in this case, kiwi fruit, which is a very, very sensitive commodity to ethylene. Basically, we are showing here in the results of one experiment. We did, in the top panels, we have fruit that was held in a cold store for 2 months. The bottom 2 panels represent fruit that was stored for 4 months in the cold room. And then we transfer this fruit to 20 degrees to allow it to ripen normally. And we are showing on the left side the production of ethylene, the ripening hormone. And the red lines represent the ozone-treated fruit, and the black lines represent the control. And it is very clear that there was a strong reduction in the production of the ethylene when we had ozone in the cold room. Also, it's interesting to know that there was a reduction in the metabolic activity of the fruit, so the fruit that was stored in the presence of low concentrations of ozone, it was 0.3 parts per million. This fruit had lower respiration rate. So in these graphs, following kind of the same experimental design, I'm showing you, in this case again, these cell wall degrading enzyme, polygalacturonase, and other enzymes that are related to the softening of the fruit were also inhibited when we were introducing small amounts of ozone in the cold chamber. Finally, on the right panel, I'm showing you the expression of 2 genes that are crucial for the biosynthesis of ethylene. They are called ACC synthase and ACC oxidase. And it's clear that there was a reduction in the expression of the genes. So the take-home message for this second story is that ozone reduces ethylene in cold storage. For a long time, we have known that one of the main mechanisms is just a direct oxidation of the ethylene that may be in the environment. But also in this work, we show that there was an effect on the internal production of ethylene on the fruit, and this end up with a delay in the ripening process. So finally, I'm going to briefly comment on some work we have been doing in the last few years. This is related to the modulation of light in the field. Probably all of us know that fruit production is being challenged by climate change. In the last few years, at least here in our country, in the palm fruit production zone, there is a clear increase in the use of these hail protection nets. They may protect the trees against hailstorms, and also may be useful to protect against excessive temperature or irradiation. So we wanted to ask in this project whether we want to know whether or not the fruit was exactly the same if it was grown with or without these nets. So we did some work on pears and apples. I'm going to show you today the results we had on pear fruit. So this is just showing that if we had these protection nets, there was an interception of radiation. So there was a reduction in the radiation received by the plants for around 20% most part of the day. However, this didn't affect the growth of the plants. So the plants grows as well as the control. And then we had some interesting results because this is a physiological disorder which is called sunburn. You see this kind of burns on the peel. And if you had the nets, we did this experiment during 2 seasons, and it's clear that there was a reduction in the severity of the disorder. Also, there was a reduction in the incidence. So the number of fruits that were having this sunburn problem was much lower. So we were happy with that. and then we wanted to know that the fruit was kind of similar to the control. I'm not going to go into whole detail, but we will look at the fruit size, color, the firmness, sugars, and acidity. And in general, at harvest, there was not difference between control and hail net brown fruit. So that was okay. But then we wanted to know what happened when we put this fruit in the cold storage for 5 months. And we find a kind of interesting result that the growers need to consider. This is another physiological disorder that is important in palm fruit, which is called scald or surface scald. This is generated during post-harvest storage. We found in this case that there is an increase in the susceptibility of the fruit that was grown under the net to post-harvest scald. So this is kind of very important, especially if we are planning to store the fruit for a long time. We know that the fruit look the same, the chemical composition, at least the quality attributes are similar, but the post-harvest behavior is not exactly the same, and they may be more susceptible to these disorders. So to finish up with this story, we can say that climate change is acknowledged by all of us. It is affecting fruit production, and these crop protections are increasingly used. However, we need to be aware of how they may affect the quality and post-harvest responses of the fruit. So having said that, I'd like to thank all the people that was involved from the University of La Plata in Argentina. We did most of the UV work. The people in INTA, Argentina, that made a collaboration with us to work on the shedding nets. And finally, George Manganaris from Cyprus University, and Carlos Crisotto and Yanis Mina from the University of California, Davis, who collaborate with us with the ozone studies. So thank you very much for your attention, and I would be very happy to answer any question you may have. Thank you.
Thank you, Dr. Vicente, for that insightful presentation. Next, we now welcome Ms. Du Fengling's presentation.
Dear experts and colleagues, I'm a representative from Leapfrog LDF Technology Company. In the next 15 minutes, I will explore with you the technology of high-pressure processing HPP, a cutting-edge non-thermal processing technology that is reshaping the landscape of food processing, pharmaceutical sterilization, and the broader health industry. This presentation consists of 3 parts. First, LDF company introduction. Second, typical application. Third, market development. First, LDF company introduction. LDF technology is located in the National Economic and Technological Development Zone in Taiyuan, Shanxi Province. The company is a national high-tech enterprise specializing in the R&D, design, manufacturing, and production of HPP equipment. Company owners such as National High-Tech Enterprise, Specialized and Innovative Enterprise, Private Science and Technology Enterprise, and so on. With 21 years of experience in the ultra-high pressure field, the company holds 58 independent intellectual property rights and over 100 technical know-how. LDF technology has obtained ISO 9001, ISO 14000, and ISO 45001 management system certification, and its product design and manufacturing comply with ASME U3 international standards. No pictures are factory and office space. About company R&D history. Our HPP project was established in 2005. In 2018, we manufactured the first 303-liter equipment in China, enabling large-scale production in the food industry. In 2022, all models equipment have achieved market-oriented application. In terms of market presence, our equipment have been deployed in more than 10 provinces across China. We offer a full range of equipment, from laboratory scale to industrial scale, with proven delivery capabilities. Standards are a critical foundation for technology industrialization. LDF technology has been deeply involved in the development of HPP-related standards. In the agricultural section, we participated in the formulation of NYT 4337-2023, the technical specification for ultra-high pressure processing of fruit and vegetable juice pump and their beverages. In the machinery section, we lead the development of GBT 15299-2025 food machinery ultra-high pressure processing equipment. Those two standards provide important guidance for the standardized application of HPP equipment. Second part, typical application. HPP or high pressure processing operates on the core principle of applying ultra-high hydrostatic pressure, ranging from 100 to 600 megapascal, to a product under ambient or low temperature conditions. The pressure is sufficient to disrupt the cell membranes of microorganisms, rendering them inactive, while also potentially inactivating enzymes. Because the Intel process doesn't rely on heat, the color, flavor, and heat-sensitive nutrients, such as vitamins and antioxidants, are largely preserved. HPP technology has wide applications such as fruit and vegetable, seafood, meat products, sauce and dairy products, and so on. The most neutral application of HPP technology in the food section is in fruit and vegetable juice and pumps. HPP-treated food pumps perform excellently in terms of texture, color, and microbiological indicators, and are widely used in high-end baby food and functional food products. Those two images compare the vitamin and antioxidant retention rate before and after HPP treatment. The retention rate after HPP treatment is significantly higher than after thermal sterilization. The second important application area is prepared foods and ready-to-eat products. For example, ready-to-eat salad, ready-to-eat seafood, and cooked meat products. If those products were processed using traditional thermal sterilization, vegetable would become wilted, and meat texture would deteriorate. HPP technology, however, eliminates passages without heating, while preserving the original texture, color, and moisture of the ingredients. It HPP technology shows broad promise in the pharmaceutical and the health industries. In pharmaceutical, traditional sterilization methods for blood plasma, vaccines, and biologics often face challenges of heat-induced inactivation. HPP offers a non-thermal, highly effective alternative. In the health industry, active ingredients in functional food and nutritional supplements such as enzymes and plant extracts can return highly bioactivity after HPP treatment. Although those applications are still in research and pilot stage, their development potential is substantial. Market development. We established HPP lab to test products and packaging, determine the HPP parameters for product processing, verify the sterilization effect and the shelf life. Those images show the laboratory scale machine and the production equipment. In supermarkets across China, a great variety of HPP juice can be found: apple juice, orange juice, watermelon juice, tea juice, carrot juice, tomato juice, and so on. Not only that, but other products beyond juice are also appearing on the market, like oyster, bacon, durian pulp, meat snacks. The growth of the HPP technology market is driven by three main factors. First, changing consumer demand. More and more consumers prefer clean label, additive-free, short shelf life but fresh food. HPP technology aligns perfectly with this trend. Second, the rapid development of cold chain logistics. HPP products rely on cold chain distribution, and in recent years, China's cold chain infrastructure has improved significantly, creating favorable conditions for the commercial adoption of HPP products. Third, increased industry awareness. With the release of prevalent standards and the emergence of successful application cases, food companies have become significantly more receptive to HPP technology. Looking ahead, HPP technology faces three major opportunities. First, expansion of application scenario, from fruit to vegetable juice to prepared food, marine products, dairy, pharmaceutical sterilization, and beyond. Second, equipment technology upgrades. Large-scale, continuous, and intelligent systems are the direction of development. The development of continuous HPP system will significantly improve production efficiency and reduce per-cycle processing cost. Third, further standardization and more application-specific standards are introduced. The industrialization of HPP technology will accelerate. Dear experts and colleagues, let me conclude briefly. HPP technology is no longer a future concept confined to laboratories or theory. It has already achieved domestic equipment manufacturing, application standardization, and early-stage industrialization in China. Leadflow LDF Technology Company is committed to working with all of you for future advance in research and application of HPP technology. across a broader and deeper field. Okay, thank you for your attention. I welcome further discussion after the session. Thank you again.
Thank you, Ms. Du, for your valuable contribution. Continue our session. Let us invite Dr. Natalia Zerman.
Good morning, my name is Natalia Zerman, and I am a researcher at Food Technology Institute, INTA. First, I want to thank Dr. Noemi Sarinsky for the invitation to share our research with you. Today, I am going to give the presentation titled Application of Direct and Indirect Non-Thermal Plasma, Strategies for the Development of Ready-to-Eat Foods. To begin with the introduction, non-thermal plasma has emerged in recent years as a technology with great potential for minimal food processing. Plasma is often referred to as the fourth state of matter, making it distinct from solid, liquids, and gases. As we can see in the diagram, as we increase the energy input, moving from low energy in solids to moderate and high energy in liquids and gases, we can eventually reach an extreme energy level that leads to ionization. Therefore, plasma is essentially an ionized gas composed of ions, free electrons, and neutral molecules. While it occurs naturally in phenomena such as stars, lightning, and the aurora borealis, it can also be artificially generated from technological applications by applying an energy source such as an electric field to a gas. Now, non-thermal plasma stays cold due to a phenomenon called thermal non-equilibrium. This happens because the applied energy is selectively transferred to the electrons, leaving the heavier particles like gas molecules and ions at room temperature. As we can see in the formula and the top diagram, the temperature of the free electrons reaches extremely high levels, while the temperatures of the gas ions and molecules remain at ambient levels. This unique condition is why non-thermal plasma is highly safe and ideal for heat-sensitive, ready-to-eat foods. Regarding its mechanism of action, the process generates reactive oxygen and nitrogen species, commonly known as RONS, such as ozone and hydroxyl radicals, which effectively inactivate foodborne pathogens. Finally, from a quality perspective, this non-thermal approach successfully preserves critical quality attributes of the food matrix, such as texture, color, and antioxidant capacity. Regarding the technological setup, depending on how the plasma is generated, cold plasma can be classified into several systems, including corona discharge, microwave, radio frequency, gliding arc, and dielectric barrier discharge. Furthermore, the process depends significantly on the working gas. The gases studied include noble gases such as argon and helium, as well as complex gas mixtures. However, ambient air is the most widely used gas because it represents a cost-effective, sustainable, and highly scalable option from the food industry. Among the generation system mentioned, dielectric barrier discharge, or DVD, is one of the most developed systems. As we can see in the first figure, it operates at atmospheric pressure by placing the food between two electrodes separated by a dielectric material. A major advantage of this configuration is shown in the figure below, the ability to perform in-package treatments. Here, plasma is generated directly from the headspace gas, enabling an stable discharge and extended exposure that protects the closed hood. On the other hand, the last figure shows an indirect approach using plasma-activated water. In this system, plasma is discharged over the water surface, transferring reactive oxygen and nitrogen species into the liquid at the gas-liquid interface. This interaction lowers the pH and increases both the conductivity and the oxidation reduction potential of the liquid. This provides an antimicrobial effect when the food is subsequently immersed without ever exposing the product directly to the electrical discharge. This overview illustrates the application of cold plasma across a wide variety of food sectors. From a chemical perspective, research shows that plasma treatments actively impact the surface structure and functional groups of key macromolecules, such as proteins, amino acids, and carbohydrates. This allows us to achieve crucial objectives like microbial inhibition, enzyme inactivation, and the destabilization of volatile organic compounds. It is an eco-efficient and low-cost alternative to traditional processing, and its integration into modern production lines promises to create a real breakthrough in future food engineering. Moving from this global context to our specific experimental data, I will begin by presenting our case study 1 in packaged cold plasma treatments of minimal processed apples. Over the last few decades, there has been a marked increase in consumer demand for minimal processed fruit. Thus, the main objective is to provide convenience to consumers while strictly preserving freshness, flavor, nutritional value, and ensuring microbiological safety. However, processing inevitably triggers several pathways of deterioration. Glycine causes metabolic acceleration and physical stress, leading to water loss. More critically, it increased enzymatic and microbiological activity, compromising product safety. To counteract these factors and extend shelf life, traditional preservation strategies have relied on temperature control and chemical agents, though the latter are increasingly avoided by today's consumers. This is exactly where advanced hardware technologies become essential. Along with advanced packaging such as modified atmospheres, non-thermal technology emerge as highly effective clean label solutions. Therefore, given the potential of this emerging alternative to our conventional preservation limits, the main objective of this study was to evaluate the effect of cold plasma application on the preservation of the physicochemical quality and antioxidant content of minimal processed apples. Moving on to the methodology, this slide illustrates the processing flow for the fresh-cut Granny Smith apples. The process began with a standardized preparation, including washing, core removal, peeling, and cutting the apples in uniform slices. We implement a completely randomized 3x3 factorial design. Plasma treatment was carried out in a DVD equipment constructed by the group of electrical discharge led by Dr. Prevosto at the National Technological University. The first factor was the DVD plasma treatment with exposure times of 0, 1, and 3 minutes at a power of 100 milliwatts per square centimeter. The second factor was storage time, with samples evaluated at 1, 4, and 7 days at 4 degrees. We evaluate the impact of this treatment on color parameters and firmness, soluble solids, total phenols and antioxidant capacity, and PPO activity. Our initial set of results corresponds to the chromatic parameters. On the left, we have the L parameter, represented blindness, and on the right, the A parameter, which indicates the green to red coordinate. Regarding lightness in general, L values from control samples were lower than those for the treated sample. Although these within the treatments difference were not statistically significant. However, if we look at the storage time, L significantly decreased between days 1 and 4, only for the control and the 3 minutes treatment, reflecting a progressive loss of lightness. For the A values, by the day 7, were significantly higher in the control samples, following an order with 1 minute and 3 minutes treatments. The control samples completely lost their greenness and shifted toward positive values, which clearly evidence the higher enzymatic browning they underwent. In contrast, the cold plasma treatments, particularly 3-minute exposure, successfully inhibit this pathway, maintaining the green coordinate significantly closer to its initial states. Next, we evaluate the impact of these treatments on soluble solids content, shown on the left, and firmness on the right. Regarding soluble solids, the application of non-thermal cold plasma did not initially alter this parameter, as no significant difference were observed on day 1. However, as storage progressed to day 4 and 7, the lower case indicate that both treated samples 1 and 3 minutes had significant lower soluble solids values than the control. On the other hand, when looking at the firmness figure, no significant difference were found among the different treatments within each specific day of evaluation. However, if we analyze the effect of storage time, a significant reduction in firmness is evident by day 7 for all samples, including the control. This behavior is standard in fresh-cut fruits, where mechanically wounding triggers a physiological response that accelerates the ripening rate and leads to progressive tissue softening during refrigerated storage. Then we evaluated the impact of cold plasma on total phenols and antioxidant capacity measured by 3 complementary methods, ABTS, FRAP, and DPPH. As you can see, the behavior of the antioxidant capacity is strictly parallel that of the total phenols across all samples. This strong correlation is expected, since most of the antioxidants in this fruit belong precisely to the group of polyphenols and flavonoids in particular. On day 1, the 1-minute cold plasma treatment significantly increased these bioactive parameters compared to the control. The moderate stress induced by the plasma not only stimulates the biosynthesis of phenolic compounds as a defense mechanism, but it also enhances their extractability. By day 4, while the 1-minute exposure remained high, the 3-minute treatment showed a significant drop. Finally, by day 7, these initial differences have flattened out, and all the treatments were statistically comparable. To fully understand the biochemical mechanisms occurring in plant tissue immediately after processing, we analyzed the polyphenol oxidase activity on day 1. As shown in the chart, the duration of cold plasma exposure is a key factor in controlling this enzyme. Apples treated for 1 minute show the lowest PPO activity, achieving a significant 20% reduction compared to the untreated control. This key inhibition demonstrates that a short exposure successfully destabilizes the activity enzyme. To sum up, the conclusions of this study is that cold plasma technology allows the preservation of the firmness and color properties of the fruit, maintaining the tissue structure but with a decrease in soluble solids during storage. Plasma treatment for 1 minute produced apple slice with lower polyphenol oxidase activity and higher antioxidant content. However, the increase in antioxidants compared to the control samples could not be maintained during storage. The full results of this study are published in the paper named Effect of In-Package Cold Plasma Treatment on the Quality of Minimal Processed Apples by Denosha et al. Implementing our work on plant matrices, the second axis of this research shifts the focus toward the meat industry. This leads us to case study 2, where we investigate the application of plasma-activated water for cured meat products. As we can see in the reactor diagram, by applying an electrical discharge at the water interface, stable reactive oxygen and nitrogen species, known as RO and S, are generated, transforming water into a powerful liquid decontaminant. This activated water provides two major advantages for meat products. First, a high microbial inactivation against pathogens, and second, a clean label curing. Because PAW is naturally rich in nitrates, it acts as an alternative organic source to develop its traditional color and safety products. In our study, we aim to establish an adequate marinating time for beef meat using plasma-activated water as a nitrate source. Regarding materials and methods, we work with bovine superficial pectoralis muscle, cutting it into standardized pieces. Concurrently, the plasma-activated water was prepared by activating 20 liters of tap water for 100 minutes at 140 watts, achieving a nitrate concentration of 276 ppm. The meat pieces were then marinated at 2 degrees using a 1-to-13 meat-to-brine ratio in plastic trays. We evaluated two formulations, plasma-activated water alone and plasma-activated water with 4% sodium chloride, testing 3 different marinating times, 6, 18, and 24 hours. After marinating, all samples were vacuum packed and stored under refrigerator at 2 degrees for 48 hours to obtain the final product. Finally, to evaluate the curing process, we measure weight variation and total yield, total heme, and nitrosamyoglobin concentrations to determine curing efficiency and the residual nitrate concentration. Our first result regarding yield and weight variation show a definite contrast driven by the presence of salts. As we can see in both charts, treating the meat only with plasma-activated water lead to weight loss and negative process yields across almost all marinating times. In contrast, the combination of plasma-activated water with 4% of salt successfully promoted water absorption during marinating, reaching the highest positive weight variation and process yield at 18 and 24 hours. This demonstrates that while plasma-activated water provides the active curing species, the addition of salt remains technologically essential to maintain the water holding capacity and ensure a commercially viable product yield. Next, we analyzed the impact on meat pigments. On the left, we can observe the nitrosoheme and total heme concentration, which directly determine the curing efficiency shown on the right. Regarding cure efficiency, the formulation with only plasma-activated water showed higher percentage across all marinating times, reaching a peak of 77.3 at 18 hours. This happens because, without the dilution effect of water absorption driven by the salt, the reactive curing species in plasma-activated water interact more densely with the heme pigments. However, looking at the indicator below, well-cured meats ideally require values close to or above 18%. Therefore, an intermediate marinating time of 18 hours with plasma-activated water and salt yields the most balanced technological outcome. It ensures a highly satisfactory curing efficiency of nearly 60% while maintaining the essential process yield and water holding capacity we observed previously. Finally, we evaluated the residual concentration of sodium nitrate in both the center and the edge of meat samples. Naturally, due to the mass transfer mechanism, the nitrate concentration at the edge is visibly higher than in the center, across all treatments, reflecting the progressive diffusion of the brine into the muscle matrix. If we analyze the timeline at 18 hours, both formulations reach a highly uniform and effective nitrate diffusion in the center. However, by 24 hours, we see a contrast. While the plasma-activated water concentration drops, the formulation with salt triggers a massive accumulation of nitrate both in the center and in the edge. This confirms that intermediate marinating time of 18 hours is the most balanced choice. It guarantees an optimal homogeneous distribution of the curing agent in the center. To sum up, the 18-hour marinating time was identified as the optimal duration, achieving the highest curing efficiency due to a more effective nitrosamyoglobin formation. Second, we confirm that the addition of sodium chloride is a necessary technological synergy, as it successfully favored water retention, improved total pigment content, and enhanced the residual nitrate concentration. Therefore, plasma-activated water is an innovative and highly viable technological alternative for producing cured meat products with significantly lower synthetic additive content, aligning with clean label demands. Finally, its application will continue to be studied in our future research to further optimize the processing conditions and the overall quality of the final product. Well, thank you very much, and if you have any questions, I will be glad to answer them.
Thank you, Dr. Siderman, for sharing your interesting findings. Our next speaker is Associate Professor Yu Zhilong.
Hello everyone, my name is Zhilong Yu. I'm currently an associate professor at Jiangnan University in Wuxi, China. My presentation today is about nanotechnology enhanced smart packaging for perishable foods. Generally, this presentation will cover 4 key sections: research background, active packaging for fresh produce, intelligent packaging for fresh meat, and the summary in the end. Let's start with the research background. It is known that packaging is a key technology for food preservation. Traditional food packaging primarily provides physical protection, preventing mechanical damage during handling and transportation. In addition, it acts as a barrier against external factors such as oxygen, moisture, and light, all which can accelerate food deterioration. It also helps to reduce contamination from microorganisms, dust, and other environmental hazards. However, it is important to note that the ability of traditional packaging to extend shelf life remains limited, as it mainly relies on passive protection rather than active control of the food environment. Moreover, it lacks the ability to communicate real-time information on food safety and quality to consumers and retailers. To overcome the limitations of traditional packaging, smart packaging systems have been developed, which can be broadly divided into active packaging and intelligent packaging. Active packaging is designed to interact with the food or its surrounding environment. It can release or absorb functional substances to improve food preservation. For example, antimicrobial agents can inhibit microbial growth, while certain functional components can regulate the levels of ethylene, oxygen, or moisture within the packaging headspace. In contrast, intelligent packaging focuses on monitoring rather than controlling. It provides real-time information about food quality through visual or measurable signals. Typical intelligent packaging indicators can monitor key factors such as oxygen, carbon dioxide, pH, humidity, temperature, and freshness. They can also be biosensors that detect foodborne pathogens. Active and intelligent packaging enables improved food preservation and real-time monitoring of food safety and quality. Nanotechnology plays a critical role in advancing smart food packaging systems. Nanomaterials with their high surface area and tunable structures provide unique advantages for smart packaging applications. In active packaging, nanotechnology enhances antimicrobial efficiency, enables controlled release, and allows the precise regulation of gases and water vapor within the package. In intelligent packaging, nanotechnology enables the development of highly sensitive nanosensors that generate stable and accurate signals, allowing rapid and non-destructive monitoring of food quality. In this presentation, I will highlight some of our recent work on nanotechnology-enabled smart food packaging. Regarding active packaging for fresh produce, we developed a biodegradable bio-nanocomposite composed of polyvinyl alcohol, chitosan, and cellulose nanocrystals, providing strong mechanical strength and barrier properties. To introduce active functionality, copper oxide doped titanium dioxide nanotubes are incorporated, forming a visible light responsive photocatalytic system. A microporous structure with an average pore size of approximately 2.4 micrometers is engineered to enable controlled gas exchange. They are incorporated with sodium chloride and polyethylene oxide as pore-forming agents, which are later removed through washing to create interconnected pores. The innovation of this design lies in its dual functionality. It can generate reactive oxygen species under visible light while simultaneously regulating oxygen and carbon dioxide levels within the package. Interestingly, the strong antibacterial activity of the film was observed under visible light. The incorporation of copper oxide doped titanium dioxide nanotubes enables efficient absorption of visible light and the generation of reactive oxygen species, including hydroxyl and superoxide radicals. As a result, the film effectively inhibits the growth of pathogenic bacteria, including Staphylococcus aureus and Escherichia coli 0157H7. Notably, bacterial growth is almost completely suppressed after short-term light exposure. The practical performance of the film was validated through blueberry storage experiments. The results show that blueberries packaged with the developed film exhibit significantly lower decay rates compared to polyethylene packaging groups. By the end of the storage period, decay is reduced to minimal levels, and both bacterial and mold growth are effectively suppressed. Microbial analysis further confirms the suppression of dominant spoilage microorganisms, mainly bacillus and ascochiton, in blueberries. Moreover, the pores in the film allows excess carbon dioxide to escape while maintaining sufficient oxygen levels, thereby preventing anaerobic respiration. Compared with conventional polyethylene packaging, the developed films maintains lower carbon dioxide concentrations and higher oxygen levels. The film helps maintain fruit firmness and reduces visual deterioration, such as wrinkling and softening. These results demonstrated that the combined effects of antimicrobial activity and gas regulation enable effective shelf life extension of blueberries. Another study focuses on developing an active fruit packaging based on a copper-based metal organic framework, HKUST1. Although this copper-based morph shows strong potential for ethylene adsorption, its performance is significantly limited under high humidity due to structural instability and water interference. To address this issue, folic acid and silver nanoparticles were introduced via a post-synthetic modification strategy. Folic acid forms a protective layer that enhances hydrophobicity and moisture resistance, while silver nanoparticles provide additional active sites for ethylene adsorption. The modified morph exhibits enhanced adsorption performance and structural stability compared to pristine HKUST1. The ethylene adsorption capacity increased by approximately 10%, reaching 126 cubic centimeters per gram. Copper ions serve as primary active sites. Silver nanoparticles introduce additional strong interactions with ethylene molecules, and folic acid contributes secondary interactions while stabilizing the framework. Importantly, the material maintains its porous structure and crystallinity even under humid conditions. This synergy enhances adsorption efficiency. The practical performance of the modified morph was evaluated using banana storage under high humidity conditions. Compared with control and unmodified HKUST1, bananas treated with the modified morph exhibited delayed ripening, maintaining a yellow-green color for at least 7 days. In addition, the treated fruits showed reduced weight loss, lower ethylene production, and decreased respiration rates. These results indicate that the modified morph effectively regulates ethylene levels and slows physiological changes during ripening. This study demonstrates strong potential for applying moisture-stable morph-based materials in active packaging systems, particularly under high humidity conditions. For intelligent packaging of fresh meat, we developed a carboxymethyl cellulose-based colorimetric nanosensor array for real-time monitoring of pork freshness. The design integrates 3 functional components. First, anthocyanins are used as natural pH responsive dyes. However, their response is limited under single conditions. To overcome this, ionic liquids are introduced to modulate their molecular interactions, enabling a broader and more diverse color response. Second, UiO66 metal organic framework particles are incorporated into the matrix. Their high surface area and porous structure enhance gas absorption and provide abundant active sites for sensing volatile amines. Third, a hydrophobic nanosilica coating is applied to improve moisture resistance and environmental stability. The resulting material showed improved performance and sensing capability. The porous structure of UiO66 enhances gas adsorption, leading to increased sensitivity from about 32% to 40%. Ionic liquids interact with anthocyanins through hydrogen bonding and van der Waals interactions, modifying their electronic structure. This induces a redshift in the absorption spectrum and expands the color response range. As a result, the sensor array produces distinct color patterns when exposed to ammonium and volatile amines, such as dimethylamine and trimethylamine, enabling cross-responsive detection rather than single-signal output. After nanosilica coating, the water contact angle increases from approximately 75 degrees to 130 degrees, indicating significantly improved moisture resistance. This ensures reliable sensing performance under high humidity storage conditions. During POC storage, the sensor shows clear and continuous color changes that correlates well with total volatile basic nitrogen values, enabling effective deterioration between fresh, less fresh, and spoiled states. By integrating deep convolutional neural networks, the sensor achieves highly accurate freshness classification, with the VGG16 model reaching an accuracy of 99%. The system also demonstrates good reusability, maintaining stable performance over 11 cycles through reversible acid-base treatment. The integration of these advanced materials with artificial intelligence offers significant potential for next-generation intelligent packaging systems. Another study presents a bilayer colorimetric sensor array for real-time monitoring of POC freshness. The sensor is also constructed using carboxyl methylcellulose as the base indicator layer, combined with anthocyanins as natural pitch responsive dyes. To enhance their color response and stability, deep eutectic solvents are introduced to modulate intermolecular interactions and tune the molecular structure of anthocyanins. The deep eutectic solvents incorporating choline chloride with different amino acids are safer than the ionic liquids used in our previous work. In addition, a hydrophobic layer of electrospun polylactic acid nanofibers is applied, improving moisture resistance while maintaining sensitivity to volatile compounds. The sensor demonstrates high sensitivity and stability toward spoilage-related gases, such as ammonia and amines. It achieves a low detection limit of 11.92 ppm. Deep eutectic solvents interact with anthocyanins through hydrogen bonding and van der Waals interactions, modifying their electronic structure. This leads to an expanded color response range and more distinct visual changes. The PLA nanofiber layer significantly enhances hydrophobicity, increasing the water contact angles to about 122 degrees, enabling reliable performance under high humidity conditions. The sensor also shows good durability and reusability, maintaining stable performance for at least 13 cycles. The sensor system is further integrated with deep learning models for intelligent freshness prediction. During storage experiments, sensor images are analyzed using convolutional neural network. The system successfully classifies different freshness levels of POC, achieving an accuracy close to 100%. This integration enables not only real-time visual monitoring, but also quantitative freshness evaluation. It offers a green, non-destructive, and efficient solution for monitoring meat quality and safety. In summary, Nanomaterials provide superior reactivity, sensitivity, and tunability. However, safety issues and consumer acceptance remain major challenges. Although performance is validated as a laboratory skill, further testing under real supply chain conditions is required, and large-scale adoption is constrained by regulations, costs, and manufacturing limitations. In addition, packaging systems must be customized for specific food types, as universal designs are not feasible. That's all for today's presentation. Thank you for your attention. Please feel free to ask any questions you may have.
Thank you, Associate Professor Yu, for your presentation. Okay, the last presentation, please welcome Dr. Sergio Wadagana.
I would like to thank the National Academy of Engineering of Argentina and especially Dr. Nomi Sariski for the kind invitation to participate as speaker in this webinar. The title of my presentation is High Pressure Processing in Argentina, R&D Case Study and Industrial Perspective. To provide context for the high-pressure processing, I will first introduce the broader field of the novel processing technologies. These include thermal and non-thermal technology applicable to food processing and preservation. This technology shares several key characteristics. They ensure food safety and intention life with minimal impact on nutritional and sensory quality of food. Also support sustainable processing conditions. They require lower energy and water consumption and the use of electricity as the energy source. In addition to the cold pasteurization, this technology allows product development and the utilization of conventional processes of food industry. Regarding non-thermal food processing technology, this can be classified as chemical technology and physical technology. Among chemical technology, we can mention ozone, chlorine dioxide, electrolyzed water, essential oil, organic acid, and high-pressure carbon dioxide. Among physical technology, we can mention UV light, pulse light, high pressure, ionizing irradiation, cold plasma, and high-intensity ultrasound. What is high-pressure processing? This is a non-thermal food and beverage processing technique based on the application of high level of hydrostatic pressure in industrial equipment. Pressure applied is between 300 and 600 megapascal, transmitted by water for short processing time, typically on the order of a few minutes. Regarding the HPP advantages, we can mention food safety guarantee. HPP inactivate main pathogen and spoilage microorganism, meeting the requirement of the food authority. Also allow impact cold pasteurization of the product. Clean label HPP allow to reduce or eliminate the use of preservative or additive in food. Shelf life extension, depending on the product, HPP extends the shelf life up to 3 times to 30 times, while still ensuring the high quality product. Minimal processing, it provides minimally processed food, maintaining freshness of the original product. And finally, eco-friendly. It requires electricity and water, which can be recycled. Regarding HPP disadvantages, we can mention this technology does not inactivate spores. It's not effective on dry products. It can produce changes in texture or color on some products, e.g. meat, egg, or fish, and it has high investment costs. Internationally, a wide variety of high-pressure processed products are commercially available. In South America include fruit juice, dips, and purees like guacamole or cured and cooked meat such as ham or pork loin. In Argentina, however, these kinds of products are not yet available due to the lack of industrial scale equipment. In Argentina, the only high-pressure processing system installed is the one available at the Food Technology Institute of INTA. This is a laboratory-scale extended fluid power cooled with a vessel of 2-liter capacity and maximum working pressure of 900 megapascal. In this slide, you can see the different applications of HPP in food processing. Considering the pressure and temperature ranges, you can see the most common application, that is a cold pasteurization. However, other alternatives are process assistant, macromolecule modification, freeze and thaw assistance, and sterilization. Our research team has been working on high-pressure processing since 2009, with application in different food matrices, including meat and meat products, fruit and vegetable, dairy products, and also beverage and protein dispersion. Numerous doctoral, master, and undergraduate theses have been completed. In addition, several scientific papers have been published in international journals. Due to the limited time for this presentation, I've selected some of the studies we've conducted in the application of high-pressure processing technology. First, I will present you the result of the study of high-pressure cold pasteurization of raw and cured cooked meat products. Regarding the cold pasteurization of meat products, it is known that high pressure allows to achieve 6-log reduction of salmonella. In the case of Listeria monocytogenes, it's possible to achieve 4 or 5-log reduction at pressure of 500 or 600 megapascal with processing time between 3 and 6 minutes, with possible sublethal damage and recovery of injured cells during child storage. Concerning Escherichia coli O15787, this microorganism presents variability in resistance among strains. Also a high resistance in sad food, e.g. meat products. Now I'm going to present you the result of a study on high-pressure cold pasteurization of raw meat products. In this case, we evaluated the effect of high-pressure processing and the formulation on the inactivation of a pool of Shiga toxin E. coli inoculated in beef burger. We evaluated the effect of high pressure level at 400 and 600 megapascal and the burger formulation by modifying the sodium chloride concentration 1 and 2% and fat content 10 and 20%. This picture shows the lethality of the Shiga toxin E. coli strains expressed as logarithmic reduction for the 2 pressure level evaluated and the different formulation. As was expected, the pressure at 600 megapascal was more effective than pressure at 400 megapascal, producing between 4 and 4.5 reduction. In addition, a formulation effect on lethality was observed, as the burger formulated with 1% sodium chloride showed greater lethality than those formulated with 2%, regardless of the fat content. This behavior likely because the higher sodium concentration content would stress the cell, thus making the high-pressure treatment less effective. In this slide, you can see the effect of high-pressure processing on the inactivation of spoilage microbiota in beef burger. In picture A, you can see the natural microbiota count of beef burger under the refrigeration storage at 4 degrees centigrade up to 7 days. In picture B, you can see the natural microbiota count of beef burger under frozen storage at minus 18 degrees centigrade up to 35 days. In both figures, you can see that untreated samples presented count between 4 and 5, while burger treated at 600 megapascal for 5 minutes presented count below the limit of detection all over the storage under refrigeration or frozen storage. Following with the presentation of case study of cold pasteurization of raw meat product, I'm going to present you our work with beef carpaccio. Carpaccio is a ready-to-eat product prepared from raw meat from different animal species, intended for direct consumption without further heat treatment. In this case, the risk lies with the potential contamination of pathogen microorganisms associated to foodborne illnesses. In the content, high-pressure processing should be considered to ensure safety and extend shelf life of carpaccio. The main limitation of the application of high-pressure processing of raw beef is the decoloration that occurs within the pressure range required to inactivate pathogenic and spoilage microorganisms at pressure higher than 300 megapascal. In this image, you can see the effect of the increment of high pressure level on the reduction of redness and the increment of lightness of beef pieces. To minimize the effect of high pressure treatment on carpaccio color, we study the application of high-pressure treatment on frozen carpaccio and compare it with the effect on fresh and frozen carpaccio. For this, we evaluated 4 high-pressure levels: control and treated, 400 megapascal, 500 megapascal, and 600 megapascal, and 2 temperature during high pressure treatment, 0 and 5 degrees centigrade for frozen carpaccio and 0 and 20 degrees centigrade for fresh and frozen carpaccio. Regarding the effect on chromatic parameters, frozen treated samples show a lower difference in lightness and redness compared to the control than fresh treated samples. Thus, freezing prior to HPP treatment reduced the adverse effect on color parameters of carpaccio. In this picture, you can see the effect of treatment on texture. In the case of shear force value, both frozen and fresh samples treated by high-pressure processing show no significant difference with their respective contour, while work of shearing of all frozen samples treated by high-pressure processing and fresh one treated at 600 megapascal presented significantly higher values than their respective control. In this picture, you can see the effect of high-pressure processing on aerobic total count of fresh or frozen carpaccio. In the case of fresh carpaccio, maximum ATC reduction observed was 5.24. This was higher than the reduction of ATC observed for frozen carpaccio, which was 4.11. The lower effectiveness of high-pressure processing in the inactivation of microorganisms in frozen samples would be associated with the reduction of food water activity by freezing. Now I'm going to present you the result of a study about cold pasteurization of cured cooked meat products. In this study, we evaluate the combined effect of high-pressure processing with the addition of a bacteriocin in order to inactivate Listeria innocua, which is a surrogate microorganism of Listeria monocytogenes. Listeria innocua was inoculated in a slice of cured and cooked pork loin. In order to do this, we apply a factor arrangement of 2/3 factor. One factor was lactosin concentration, 0 and 105, and the other factor was the level of high pressure processing applied without treatment for hungry acid hungry. After the treatment, samples were stored at 4 degrees centigrade during 40 days. In this slide, you can see the evolution of Listeria innocua count during 40 days of storage at 4 degrees centigrade. Treatment at 400 megapascal and 600 megapascal were effective in reduced count immediately after treatment, but count recovered during storage. Only the combined treatment of lactosin and 600 megapascal for 5 minutes effectively maintained Listeria innocua count below the limit of detection over 40 days of storage at 4 degrees centigrade. In this picture, you can see the evolution of count of total aerobic mesophilic bacteria and lactic acid bacteria in cured cooked pork loin during 40 days of storage at 4 degrees centigrade. Absence of count for both kinds of microorganisms was observed in samples treated at 400 megapascal or 600 megapascal alone or combined with lactosin LL405 during 40 days at 4 degrees centigrade. In this slide, you can see the evolution of total aerobic mesophilic bacteria, psychotrophic bacteria, Enterobacteriaceae, and lactic acid bacteria count of cured and cooked pork loin treated at 600 megapascal during 5 minutes storage at 4 degrees centigrade during 150 days. At the end of the storage, control samples show count significantly higher across all determinations compared to the HPP-treated samples. Considering the cold pasteurization of raw and cured and cooked meat products, we can conclude that high-pressure processing effectively inactivates pathogens and reduces spoilage microbiota in both raw and cooked cured meat products. In the case of E. coli O157X7, it was possible to achieve 4 or 4.5 log reduction in burgers treated at 100 megapascal for 5 minutes. Spoiled microbiota reduced below the limit of detection. In the case of Listeria innocua, 6 log reduction in cured cooked pork loin, but regrowth during storage was observed. In this case, bacteriocin helps control injured cells and prevent growth. Finally, I'm going to present a different application of high-pressure processing than cold authorization. In this case, it involves a high-pressure processing assisted process, specifically accelerating the ripening of the Argentina rellenito cheese, one of the most exported Argentinian cheeses. Cheeses were manufactured at the pilot plant of the Inter Rafaela experimental station. It was necessary to prepare cheeses with 5 cm in diameter to fit into the HPP equipment bucket. The cheeses were treated in the high-pressure processing system available at the Food Technology Institute of INTA. Experimental design with pressure level of 100 and 400 megapascal and processing time of 5 and 10 minutes was applied. Ripening was carried out at 14 degrees centigrade up to 90 days. A complete analysis was performed at day 1, 45 and 90 days. In this figure, you can see the evolution of ripening index during ripening time. At the onset of the ripening, treated cheese were not significantly different from the control. At 45 days, sample treated at 400 megapascal exhibited a significant higher ripening index than the other treatment. At 90 days, sample treated at 400 megapascal during 10 minutes show a significantly higher ripening index than those treated at 400 megapascal for 5 minutes. Thus, HPP treatment enhanced primary proteolysis in rellenito cheese, indicating the increment of activity on non-microbial enzymes such residual coagulant and plasmin. In this table, you can see the plasmin and residual coagulant activity in processed cheeses. Plasmin activity had a tendency to decrease with the ripening time. Differences were not statistically significant. Cheeses treated at 400 megapascal for 10 minutes had significantly higher plasmin activity than did the control and the other HPP treatment. Residual coagulant activity increased significantly in all cheeses during ripening. High-pressure processing treatment had no detectable effect. Regarding the sensory analysis results, at 45 and 9 days, cheeses treated at 400 megapascal show higher cell titrate intensity, and those treated at 400 megapascal for 10 minutes show a more pronounced typical flavor. Considering the conclusion of the part, high-pressure processing is a promising tool to accelerate the ripening of the Argentina rellenito cheese. However, pressure level and processing time must be optimized, and sensory impact have to be evaluated, particularly overall consumer acceptance. Finally, I want to thank the group of researchers, scholarship, and technicians who participate in these studies. Thank you for your attention.
Thank you, Dr. Wadanagana, for your presentation. Okay, last, we will open the section of interactive discussion. Panelists are welcome to pose questions or share comments.
Sorry, Junfei, I would like to thank to the participant, maybe, please. On behalf of the organizers of this webinar, I would like to sincerely thank our speakers from China and from Argentina for their insightful presentation and for sharing their expertise with us today. Your contributions have added great value to this webinar, and we truly appreciate the time and the effort you dedicated to preparing and presenting the results. Thank you very much.
Okay, thank you.
Is there any question?
Hi, Dr. Sherman. Actually, I have a question about the cold plasma technologies. As you mentioned in the case of fresh cut apple, I see that you found that for 1 minute treatment, the activity of polyphenol oxidase actually decreased. But after 3 minutes of treatment, actually there's no significant difference compared with the control. I see it's a very interesting phenomenon. Can you explain why it happens?
Okay, hello. Okay, sorry because my voice is very bad. This assays was performed by a co-worker named Denosha Gabriela. So I presented all her results, but I can explain specifically why that enzyme, the PPO, has a different behavior at 1 minute and 3 minute plasma treatment. But I can send the question to her so she can answer you about this behavior.
Yeah.
Is that okay for you?
Okay, thank you. There's another question about, is there any commercial application of cold plasma in the food industry in Argentina right now?
As far as I know, no.
No,
At the moment, no.
No.
Okay, thank you.
Commercial application.
It's a new technology and it's in a phase of investigation.
Okay,
It's
thank you.
not
Yeah.
at the industry yet.
Yeah, I see it's widely used for water treatment, but I didn't see any applications in the food industry right now.
No yet.
Yeah. If possible, I would like to offer a brief comment for this webinar. Firstly, I'm delighted to join this webinar on new food preservation methods. Throughout my career over 3 decades in post-harvest R&D in fresh fruits and vegetables, I have witnessed significant advancements in this field. I find that today's presentations from both universities and industry very interesting and truly inspiring. HPP, plasma, MAP, and smart packaging mentioned in today's presentations are promising emerging technologies for food preservation. Although I have not yet had the chance of visiting Argentina, I hold a great respect for its stature as a major South American nation and its abundant agricultural resources, many of which can be now found in the Chinese market. Looking ahead, I look forward to engaging in deeper dialogue with our Argentina colleagues to initiate some possible collaborations in near future. Those are just a few of my thoughts. Thank you.
Thank you. It seems that there are no questions.
Yeah. Okay. I would like to expand my sincere appreciation to all of our speakers for your excellent presentation. This brings us to the conclusion of today's webinar. Thank you all for your participants and hope to see you at the next event. Thank you.
Okay.
Okay.
Bye.
Bye-bye.
Thank you very much.
Bye.
Thank you.
Thank you.